us recall that in the last lecture we have studied ideals in a commutative ring and operations on the ideals, and then we have used ideals to construct a new ring from the given ring, and that is called residue class ring of the ring by the ideal we were under consideration. Now, today I will define and study some special ideals in a ring. So, these are called prime ideals and maximal ideals. There are two types of these special ideals. As usual, let us denote A to be ring, and let me remind you, in the last lecture I have introduced a notation for I of A. This is the set of all ideals in A, and on this we have this operation plus intersection product and one more, that is colon. These operations we have defined, and then some other properties I will write in some of the exercises. But today, so let us define first. An ideal P in A is called a prime ideal if, so let me just remind you, this prime ideal will be a generalization of a prime numbers. See, we have studied prime numbers right from the school. They are in the ring of integers, and these ideals, prime ideals, will correspond analog of the prime numbers. So, the definition one can guess. So, an ideal P is called a prime ideal if, first of all, P is not a unit ideal, and if A times B belongs to P, a product belongs to P for A comma B in A, then one of them should belong to P. A belong to P or B belong to P. So such an ideal is called prime ideal. Let us see some examples first. Immediately after the definition we should see some examples. So, some examples. In the ring Z, we know any ideal is a principal ideal generated by a natural number. The ideal Zn, where n is a natural number, is prime if and only if n is a prime number. So, how is this? So, let me just, so one has to get used to it. First of all, when you say, I should say a proper ideal, ideal Zn which is not Z, that means n has to be at least 2. Okay, so what do you have to check? It's a product A times B belongs to Zn. So, I am proving first if it is a prime number, then it is a prime ideal. So suppose the product belong to this. What does that mean in terms of divisibility condition? That means this AB is a multiple of Z, multiple of N. AB equal to C times N, but this is where C belongs to Z. But this is if and only if N divides AB, but this implies N divides A or N divides B, since N is a prime number. And obviously the prime numbers are okay. So we have proved if it is a prime ideal, then it's generated by a prime number. Conversely, if you have a prime number, then we have this property. Therefore, this is actually if and only if. This is if and only if N is prime. So in Z we know all the prime ideals. They are precisely generated by the prime numbers. Okay. All right. So some more example. 2. Suppose you take any integral domain. So A, ring A is an integral domain if and only if the ideal 0 is a prime ideal. So let us check this again. So I am checking if it is an integral domain, then 0 is a prime ideal. So I am proving this way. So I want to prove 0 is a prime ideal. So let us take a product AB belongs to ideal 0. But that means AB is 0, because 0 is the only element in the 0 ideal. But you are in an integral domain, so there is no non-zero 0 divisor. That means, so this should imply either A is 0 or B is 0, since in an integral domain there are no non-zero 0 divisors. So that proves this way. Conversely, this way. That means we are assuming 0 is a prime ideal and you want to prove A is an integral domain. So how do you prove some ring is an integral domain? You have to check that there is no non-zero 0 divisor. So suppose A is non-zero element and suppose A times B is 0, then what do you want to show? And we have to show that B must be 0, because if B were non-zero, then this A will be a 0 divisor. So but AB 0 means, this means A times B belongs to the ideal 0. But then 0 is the prime ideal. So product of elements belong to the ideal 0, 0 is the prime ideal. So that should imply either A belongs to 0 ideal or B belongs to 0 ideal. Since ideal 0 is a prime ideal. So but this means A is 0 or B is 0. So that in an integral domain 0 is a prime ideal. So third, so therefore in particular in the ring Z mod n, where n is a natural number and not prime, not a prime number. Zero is not a prime ideal. Because we know, because if n is not a prime ideal, then Z mod n is not an integral domain, therefore 0 cannot be prime ideal. Okay, so third example. Now let us take a field, K is a field, and let us take a polynomial ring over K in one variable. Then just look at the ideal generated by x square plus 1. This is an ideal generated by x square plus 1 in Kx. Now if K equal to R, this ideal is, if K equal to R, then this ideal generated by x square plus 1 is a prime ideal. That is very easy to check, but if K equal to C, then it is not prime ideal, then it is not a prime ideal in Cx. This is very simple because look at the product x minus I times x plus I, this is equal to x square plus 1, which belong to the ideal generated by x square plus 1, but none x minus I or x minus x plus I, they belong to, so none of them belong, so both of them, but both doesn't belong, simply because if they belong, then the degree, this is 1, degree this is 2. So, this is a multiple of this, will mean the degree is bigger equal to 2, which is not true. Alright. So, more generally, this I will do it later also. So, some more prime ideal, let me see if I have some more. Okay. So, anyway, so I will give some more examples once we have enough vocabulary. Now, the second definition. So, before I go on, I will write the set of prime ideals in the ring A is denoted by this symbol spec A. This is called a spectrum of A. Prime spectrum of A. The prime spectrum of A. Let me just make a comment here that this is the same word spectrum which usually we come across in physics. So, there is a nice connection between the spectrum the word from physics and this spectrum. I will try to digress it when we have enough vocabulary in this course. So, this is the set of all P in the ideal of A such that P is a prime ideal. In A. So, obviously, this ideal unit ideal A that does not belong to the spectrum, and ideal 0 may or may not belong. We have seen both the cases. In some cases 0 belongs, and in some cases 0 does not belong to the spectrum. All right, and this will be one of our main object of study in this course. One has to study the prime spectrum and gain a knowledge about the given ring. So, that is how it is. So, the first very important result we will need, that this is indeed a non-empty set. If it is empty set, again we will have nothing to study, and then our goal of studying algebra with geometry and geometry with algebra will not take place. All right. Another very important definition is, we will soon prove that this is a non-empty set. So, definition. Now, this is the definition of a maximal ideal. An ideal M I of A in the ring A is called a maximal ideal. In A, if there should not be bigger ideal in the ring than this M, but of course, the unit ideal is the biggest ideal that way. So, you should avoid unit ideal. So, if M is a maximal element in the ordered set, I A, remove A from that unit ideal, and this is an ordered set with respect to the inclusion order. So, this is my ordered set, and this M should be a maximal element there. So, what is a maximal element in an ordered set? That means there is no element bigger than that, it is in that set. So, that is, if M is contained in some ideal A contained in A with ideal A is ideal in A, then either this Gothic A should be capital A, that is it is a unit ideal, or it is equal to M. So, then either A equal to M or A equal to the unit ideal A, then you call it a maximal ideal. Now, so some examples as usual, that will be always our strategy. So, example, one 0 ideal. So, I will not write any bracket. So, the ideal 0. So, one way it is clear from our writing what we are considering. This is, so where am I taking, what is my ring? So, I should specify my ring also. In the ring of integers, this is not a maximal ideal. In Z. So what should we produce? We should produce a bigger ideal, which is not a unit ideal. So since 0 properly contained in, let us say, 2z, z2, z2 is a proper ideal. One can never be multiple of 2 in z. So and this is properly contained in z. So this is not maximal in this. So therefore this is not a maximal ideal. However, if P is a prime number, then the ideal generated by P, that is ZP, is a maximal ideal. In Z. So let us prove this. Of course, later on also we will see how do you test some ideal is prime, and this will become trivial in that test. So what do we have to check? So suppose there is a bigger ideal. Suppose that ZP is here and there is an ideal in between. So we know any ideal in Z, it's generated by one element, one natural number in fact. So this looks like this. So n is a natural number. And let us assume, so what do we have to prove? We have to prove either equality here or equality here. Right? We have to prove either equality here or equality here. So let us assume one of them is not equality. Let us say this. So this is not equal means this is equivalent to checking n is bigger or equal to 2. Because if n were bigger or equal to 2, if it is equality here, 1 should belong here. But 1 is never a multiple of n where n is bigger or equal to 2. So this condition not equal to is equivalent to saying this. This is equivalent. So I have to prove equality here now. So what does this mean? This inclusion is equivalent to saying P belongs to n, P belongs to z times n. That means P is a multiple of n. So this is equivalent to checking P equal to some m times n, where m is an integer. N is a natural number bigger or equal to 2, P is a prime number and m is integer. So this equality first of all will force you that this z has to be a positive integer. Not only that, then P divides m times n. So that will imply P divides m times n, and therefore P is a prime number. So P either divides m or P divides n. But so we will say both of them are both, either of these gives a contradiction. So if P divides m, what does that mean? That means this m is a multiple of P. So m equal to some m prime times P, m prime is in Z. When you plug it in here, then we will get, so we will get P equal to m prime times P times n. But now we can cancel this, and we will get 1 equal to m prime n. But n is at least 2 and m prime is an integer, so that is not possible. So this is not possible. What about this? If P divides n, again do the same. If P divides n, so if P divides n, then P n is a multiple of P. So this is not possible. So P divides n. P divides n will mean again n equal to n prime times P. But then again you cancel and get a contradiction. So, I will just write a dot dot here. Just few minutes later we will see how to check in a better way. Okay, so that was their prime ideal. So, therefore, in this case, so I will write here. So, we have described all elements in the spectrum of Z. So, this is precisely, obviously one element is a 0 ideal, the other one is ZP. So, I should write the correct notation. This is union ZP, where P is a prime number. So, this P is the set of all prime numbers. So, like we have introduced a notation for the prime spectrum, also I want to introduce a notation for set of all maximal ideals. So, the set of all maximal ideals in the ring A is denoted by SPMZ. SPMA is called the maximal spectrum of A. All right, again the same. So, let me give some more examples. It is very important to see more examples of the maximal ideals. But before I do that, I want to check how do you test some ideal, some given ideal, whether it is prime or not. So, for that there is a nice easy test. So, that is, let us call it a proposition. Let A be a ring and A ideal in A. Then this test, then this proposition is very handy to check some ideal is prime or not and maximal or not. So, part 1, A is a prime ideal if and only if in A of course, A, the residue class modulo A, this ring what we constructed yesterday, this ring is an integral domain. Two, A is a maximal ideal in A if and only if A mod A, this also I keep calling it A modulo this A modulo Gothic A is a field. So, let us prove this. Proof. I am proving one and that too this way. So, that means we are assuming A is a prime ideal. And then what do you want to prove? So, suppose A is a prime ideal, then write in a corner somewhere that to prove the residue class ring, this is an integral domain. That means what do you want to prove? If product of two elements is 0, then one of them is 0. This is what we want to prove. Okay. So, first of all it is a prime ideal, therefore A is not A by definition, and therefore this is not a 0 ring. A mod A is not a 0 ring. This is a non-zero ring because it's a proper ideal. And now you remember yesterday we were denoting the elements of this ring by cosets A plus A. But I will denote this by A bar. So, elements of the residue class ring are denoted by bars of the small letters. And what do you want to prove? If it is if there are two elements A bar and B bar in A mod A, and A bar B bar is 0, 0 bar in A modulo A, then I want to do one of them is 0. But what does this mean? The way we have defined the multiplication in this residue class ring, this is same thing as AB bar equal to 0 bar. What are when are the two elements equal? When the difference belongs to the ideal. So, this is equivalent to checking AB minus 0 that belong to the ideal A. But A is given to be a prime ideal and the product belong there. Therefore, either A in A or B in A. But that means, so this means what? This means A bar is 0 bar or B bar is 0 bar. This is equivalent to saying this. Same. Two bars are equal means the difference belong to the ideal. This is if and only. So, that proves if A is a prime ideal, then A modulo A is an integral domain. Conversely, if A is an integral domain, actually you can reverse this, all these arguments. So, I will leave it, I will just say check this. Check this implication. Okay, now 2. I want to prove A is a field if and only if A is a maximal ideal. So, if A is maximal ideal, that means first of all A is a proper ideal because it is a maximal element in IA minus singleton A. So, this is not a unit ideal. And now what do we want to check? I want to check that A mod A is a field. That means what do I have to check? So, that is I have to check that every element A bar in A by A is in A has a inverse. That means what? We want to find B in A such that A bar times B bar equal to 1 bar. This is what we want to find. Alright. So, A bar is here and non-zero. I should have written A bar is non-zero. A bar is not 0 bar. But what does that mean? That means, so this is equivalent to saying the difference is in the ideal. So, A minus 0, that is A is in the ideal, not in the ideal, not 0. So, the difference is not in the ideal. So, this is not. So, obviously what do I consider? Look at A here and take ideal generated by this A and that small a. So, that is plus. So, this is clearly an ideal which contain all this and A also. So, this is the smallest ideal which contain the Gothic A and small a. So, this is, and this A is not here, that means this is proper. So, this is a bigger ideal, this is because A is not here. but then this is an ideal in A. So, because of the maximality of A, this has to be equality here. This has to be equality, but that will mean, so that means 1 here is a combination of somebody in A and some multiple of this small a. So, that is 1 equal to some A prime plus B times A for some B in A. But now when you read this equation modulo A, then what do we get? Then we will get 1 bar equal to bar of this A prime bar plus B A bar, which is A prime bar is what? A prime is in the ideal A. I forgot to write here, this one is in the ideal A. So, therefore, this is 0. So, 1 bar equal to, no, so this, so this A bar A1 A prime bar is 0. So, 1 bar equal to, this is B bar times A bar. So, I produce a inverse for A bar. So, therefore, so this proves A mod A is a field, and converse is similar. So, I will not prove the converse. Alright. So, we have a easy way to test some ideal is prime or not. You go modulo and then check that it is prime or not. So, just one example and then, so example, before I write an example, maybe better to write one corollary. So, corollary, let A be a ring and P be a prime ideal, or not P, M. M is a maximal ideal, SPMA. Then M is also prime ideal. So, in other words, every maximal ideal in A is also a prime ideal. Converse, we have seen it is not true, because 0 is a prime ideal in the ring of integers, but 0 is not a maximal ideal there. So, this is in symbols SPMA is contained in spec of A. So, that is this in symbols. Proof is very simple. Let us finish it off. Proof: M is a maximal ideal, that is given. So, therefore, A modulo M is a field by the proposition second part, but once it is a field, it is also an integral domain. So, therefore, every field is an integral domain, therefore, A by M is also an integral domain. Therefore, again by proposition, so this is by proposition again, P M is a prime ideal. This is by proposition, and this is also by proposition. This is by part 2 and this is by part 1. So, we have proved that every maximal ideal is prime. Now, the question what we were thinking, that we need this set to be non-empty. So, actually we will put this set, we will prove that this set is non-empty, and that will be very important for us, because then we will have a nice flow of many ideals which are maximal ideals, which are prime ideals, and so on. and I will continue in the later half by many more examples is in some special rings, mostly geometric examples. So, we will meet after the break. Thank you.